Hi everybody! Today we are going to start our unit on absolute value functions by learning how to graph them. In order to do that, in this video you're going to learn how to apply knowledge of the absolute value parent function and then also describe the functions that we're graphing as transformations of that parent function. So let's go ahead and get started by looking at the absolute value function. So the absolute value function, if we call it f of x, is equal to the absolute value of the input x. Now what this means is that there are two pieces to this function. If you put in a number x that is greater than or equal to 0, so if you put in 0, 1, 2, 3, 1/2, anything that is greater than or equal to 0, then the absolute value function just keeps that number as that positive number. So if I put in, say down here, 2 into f of x, so I'm finding f of 2. The absolute value of 2 is just using this top piece because it is greater than or equal to 0, 2. Oops. The other piece is that if I put in a number that is less than 0, so a negative number, then it's going to take the negative of whatever that number it is. So if I put in -2 this time, so if I find f of -2, that means I'm taking the absolute value of -2, which means I'm using this piece of my piecewise function, which means it's negative from the rule, -2 from my input. And -2 is just +2. So the absolute value function makes every input value, every x value that you put in, positive. So if I'm finding the absolute value of -1, that's going to be -1 or +1. If I find the absolute value of 0, we're using this top piece again because x is equal to 0, so I'm just using the x values, so that's just 0. And if I take the absolute value of 1, it just stays +1. So these two pieces allow me in a very mathematical language to use the absolute value function to take the every number input and make it positive because it's the value of it, the absolute value of it, the positive value. So what I've done here in this chart now is that I've created a bunch of ordered pairs. I have my x and I have my y. So at -2 we found that the y value is going to be 2, so I'm going to graph that. And then at -1 it will be +1, 0, 0, 1, 1, and 2, 2. So you can see here, if we connect all of our dots, that we are looking at a V-shaped graph. Let's do some review from the last chapter and answer these questions about the characteristics, because you're going to see a lot of questions like this, not just in this unit, but in most of the upcoming units. First, I want you to notice the slope of the right branch. That's this right-hand side over here. Remember, slope from Algebra 1 is rise over run, rise over run. So we're rising 1 and we're running 1 each time. So 1 over 1 means that our slope of our right side is 1. Now the domain, this left side goes all the way to the left, which means it goes to -infinity on the left, and this right side goes all the way to the right, which means it goes to +infinity. So our domain is, all real numbers. Okay. -infinity to +infinity. Now for our range, remember that's bottom to top. We do have a bottom, the bottom of the V shape. This vertex here is our bottom, and the y value there is 0. So our bottom starts at 0 with a hard bracket, and it goes up forever on both sides, so that goes to +infinity. This guy up here with the soft bracket. The vertex, we've already said, is this guy here, which is 0, 0. The y-intercept is where it crosses the y-axis. That also happens to be at 0, 0 in this parent function. Remember, zeros means x-intercept. It crosses or touches the x-axis at the vertex, which is 0, 0. If we're looking at increasing and decreasing, remember we're going from left to right. So if we look at the left-hand side first, starting on the negative infinity side, this side is decreasing, and then we start going uphill, so that side is increasing. The increasing side starts at 0, and remember we're using soft brackets only here, and goes all the way to the right to positive infinity. The decreasing side starts on the left side of the graph, so that's the negative infinity of the x-axis, and it decreases until we get to the vertex, which the x value of the vertex is 0. For the end behavior, when we look at the left-hand side of the x-axis, that's over here, the function, the y values are going to continue going up forever. The end of the function keeps rising. So that's positive infinity. And the right-hand side of the graph over here, the function is increasing, which we've already said, so the end behavior is that it's going to keep also going up to positive infinity. We're going to be using these graphs to graph functions. There's an easier way to do it than filling out this chart, so I'm going to show you that in a few minutes. And then we're going to be able to answer these questions with our pictures. This will always be the parent function, meaning just the absolute value of x, nothing fancy going on with it. Vertex is at 0, 0. And these are going to shift around a little bit depending on what changes in our equation. So let's go look at some of the possible changes now. First, I want you to be aware that there's this super helpful formula that it would be really good for you to get comfortable with. This is not a formula that's going to be provided for you, so it's one that I would memorize if I were you. You'll notice that there are our absolute value bars, and we have our x, and then there's all of this other stuff. There's the a value, the h value, and the k value. We're going to break down each one of these separately, and then we'll put them all together to graph some of the ones that have lots of changes in them. Each of these variables is going to be a number when we look at an equation that you're graphing, and they're each going to transform the parent function that has the vertex at 0, 0 that we just looked at. So let's look for vertical shifts first. If we are looking at the absolute value of x plus 0, so we're looking at this k value here. Nothing is being changed with this one. So I'm going to pull up my calculator here so we can look at that picture. You can see that I've already got this one programmed into my y1 just to save a little bit of time. So if you were going to do this in your calculator, which you will often, to get the absolute value bars, you're going to hit the math button, and then you're going to go over to where it says num for number, and that first option is abs. So when I choose that first option, it gives me the bars. Then I can type in my x, I can type in any h values, and I can go outside to type in my k value as well. I'm not going to use that one since we've already got this one up here programmed in. I'm going to go ahead and hit graph. Maybe. There we go. So that we can see the shape. Notice that the vertex here is at 0, 0. This is just like that graph that we just looked at because it is only the absolute value of x. There's no number affecting it because 0 doesn't change anything. So we have our vertex there. The vertex we just said was at 0, 0, and the k value is this number being added onto the outside. It's 0. So now let's look at changing that. Let's look at the absolute value of x plus 2 on the outside of the absolute value bars. So I'm going to leave the parent function there so we can see how it moves. What we're looking at is what changed when I graph this y2, which is going to be red. So let's hit graph again now that I've turned it on. What do you notice? What moved between the black one and the red one? What I see is that the vertex, instead of being at 0, 0, it moved up now, and that shifted everything up. And it looks like if I'm just eyeballing it, that's 1, 2 units. So my graph then went 1, 2 units up. Oops. There's my new vertex, and then it's still that same V shape. So my vertex now is 0, 2, because the y value is what changed, and the k value, the thing being added on the outside of the absolute value bars, is positive 2. So notice that when this k value changed from 0 to 2, it moved the V-shape origin up 2 units. Let's look at one more. Let's look at this guy over here. I am going to hide that red one that we just did so it doesn't confuse us, and I'm going to turn on the absolute value of x minus 5. It's going to graph in blue this time. Okay, so there's my black parent function, and look what happened here. Now our vertex moved down the y-axis, and it looks like 1, 2, 3, 4, 5 units down, which is interesting because over here, look at what the k value is. It's minus 5 on the outside of the absolute value bar. So my vertex is there now. There's my V shape. The vertex now is 0, negative 5. The k value is negative 5. So let's summarize. The k value moves the parent function up or down. Oops. Because in the one where the k value was positive 2, it moved it up 2, and the one where the k value was negative 5, it moved it down 5. And that is always going to be true of the k value, the number being added on outside of the absolute value. It's always going to move the vertex up or down from wherever it is. Okay, so let's look at horizontal shifts now. When we look at horizontal shifts, we are looking inside the absolute value bars at what's being added or subtracted from the x. Now, I do want you to notice in our formula up here, we're looking at the h value here, and there's a minus sign in this formula. So that is going to make things a little bit hairy at first. Once you get the hang of it, it'll be totally fine though. So this time, rather than using the calculator, I want to show you with Desmos what these look like. So I'm going to exit out of my show for a second and pull up Desmos, which I've already programmed in. Okay, so you'll see I've already got the first absolute value function plugged in. This is the absolute value of x minus 0. And all of that is inside of the absolute value bars. So notice that my vertex is still here at 0, 0. Let's go in and answer some of these questions. So I've got a vertex at 0, 0, because this is what my graph looks like on Desmos. And the h value, that's the number being added or subtracted inside, is 0. So now let's look at this next one, the absolute value of x minus 1. And again, I'm going to leave the parent function and let's add in our next equation. So notice what happened to the vertex. The vertex moved over. It's over at 1, 0 now. Let me zoom out just a little. So yeah, okay, so that makes it a little bit easier to see without the half points. So we moved over 1 unit to the right in the positive direction. So if we look at what's going on over here and draw a rough sketch, we have 1 unit to the right. That's where our new vertex is. And it went to the positive 1, but notice this was a negative 1. And that's what I mentioned earlier about the formula having that minus sign inside. If we do minus negative 1, we get positive 1. So that means the h value that we're working with can't be negative 1 because this says minus 1, not plus 1. If we put in a positive 1 there, if we put in this guy, x minus positive 1, that gives us the actual equation that we're looking at. So our h value, we are going to always change the sign on the value that is inside the absolute value bars. So our vertex from our picture is 1, 0. Our h value is not -1, but the opposite of that, +1. By flipping that sign, it tells us, h tells us, what the x of our vertex is. So let's look at this next one. We're doing the absolute value of x plus 3. So I'm going to pull these back up. I'm going to hide the one we just did, and let's look at the absolute value of x plus 3. Okay, what do you notice here? It was a +3, but my vertex moved 1, 2, 3 to the left, and the vertex is now -3. So that same idea is holding firm here. We have 1, 2, 3 to the left for our absolute value function. The vertex is -3, 0, which means that again our h value changed signs. Because it's a +3 in the equation, we're going to have a -3 as our h value and our vertex. So we're doing the opposite of whatever sign for the h value that we see in the absolute value bars. So in summary, the h value moves the parent function from the vertex either to the right or it moves to the left. It moves it horizontally. Okay, so the last value that we need to talk about is this a value here. Notice that the a value is being multiplied out front. It's different from the k, which is always going to have an addition or subtraction sign. Whenever we have an a value, it's going to be a times the absolute value bar quantity. So let's look at several examples because I think dilation tends to be the hardest part for students. This first one is the 1 times the absolute value of x. So let's look at that on our handy graph. I'm going to hide both of those and pull up just the 1 times the absolute value of x. Notice that the vertex is still at 0, 0. The slope of the right-hand side is still rise 1, run 1. This is just our parent function. Remember, when you multiply by 1, it doesn't actually change anything. 1 times 2 is still just 2. 1 times 4 is still just 4. 1 times the absolute value of x is still just the absolute value of x. So that means our vertex is still at 0, 0, and our slope is still rise 1, run 1. Now, that means our vertex is 0, 0. And do you notice anything about the a value here of 1 and the slope that we just did? Do you notice that the slope was 1 and the a value was 1? The slope of that right side and the a value are the same. So let's look at this next one now where our a value changes to 2. So let's see this guy. All right, notice that we got a V shape that is more narrow. The vertex did not move, but look at the slope. The slope is rise not just 1, but 2 and run 1. So if we're thinking about that here, if we have a vertex and we're rising 2 to run 1, and then we're rising 2 more to run 1, we're getting a much more narrow V this time. It's getting stretched or pulled upwards. The two ends are getting pulled together. So the vertex is still 0, 0. A value didn't change that, but this a value of 2 changed the slope of the right side to also be 2. What do you think an a value of 1/2 being multiplied 1/2 times the absolute value of x is going to do? Do you have a good guess? Let's look at the picture and see if you're right. All right, so were you thinking that the a value was going to change the slope? Because if so, you're right. Look at how wide this red absolute value got because of that 1/2 slope. Instead of rising 1 and running 1, 1/2 means you rise 1 and run 2. Rise 1, run 2. So our slope got much wider. It got flatter, if you will. We are going to compress it or squish it down. So it's kind of like setting something heavy on top of this black parent function to push the sides down to be a more wide V shape. So let's record that. Our vertex did not change. It's still 0, 0. Our A value was 1/2 this time, which means our slope on the right-hand side was 1/2. Our vertex was still there, but we rise 1, run 2 this time. Rise 1, run 2. And we make our other side match. Rise 1, run 2. Rise 1, run 2. So we get a much wider, sorry, that point was a little messy, a much wider V than our original. We get what's called a compression. In this one where we had the 2, our slope got more narrow. We're going to call that a stretch. And specifically, these are changing vertically. We have a vertical stretch because the stretch gets pulled up vertically, and we have a vertical compression because the V shape gets vertically pushed down. All right, so let's look at these last two that have a little bit more going on in them. First, I want you to notice that the A value in our next equation is -1 times the absolute value of x. So our A value is -1. That means it's going to change our slope again. Let's look at how using Desmos. So I'm going to leave the parent function, but I'm going to unhide this one. What happened there? The vertex is still the same, but notice that instead of rising 1 and run 1, we fall 1 and run 1. So that's a -1/1 for our slope now. So that negative A value changed my slope from +1 to -1, and it made the V shape, the absolute value function, open down instead of up. So that negative A value left the vertex the same, but changed the way the V-shaped opened. It's going down now instead of up like our original. What do you think an A value of -2 is going to do? What's the slope going to be? What's the vertex going to be? And which way is it going to open? Let's look at the picture. Okay, so our vertex is still 0, 0. Our slope is not falling 1 and running 1 anymore. It's falling 2 and running 1. So that means we're going down 2, -2, and over 1. That then means that we had that vertical stretch happening, right? Because we have that 2 value, but it's also opening a different way. It's opening down this time. So we are falling 2 and running 1. Falling 2 and running 1. So now we have a more narrow V shape. Our vertex is still 0, 0. That is not changed. That -2 A value changed my slope on the right side to be -2. So this one is a vertical stretch because it got more narrow. It got pulled down this time, but it's still that vertical pulling on it instead of pressing on it. So let's do a summary. If the A value is greater than 0, that means it's like this top section up here. We have A values that are all larger than 0. It opens up. If the A value is less than 0, like these bottom two down here, it opens down. And if our absolute value of A, so the value of it, disregarding any negative signs. If it's greater than 1, so we're looking at ones like this middle one and this middle one, because the absolute value 2 and negative 2 is both positive 2, that's when we're getting a vertical stretch. A helpful way to remember this is anytime you have an a value that's an integer or an improper fraction, something like 3 over 2. We rise 3, run 2. Those are always going to be stretches. Integers will make us more narrow and improper fractions will make us more narrow. If the absolute value of the a value is between 0 and 1, meaning it's a proper fraction, like 1/2 or 1/3 or 1/4, the graph is going to vertically do what this third one did. It's going to compress. All right, now this vocabulary of stretch and compress is something we're going to come back to often. It's going to take a little bit of time to get a handle on it, but we will get there. Let's do 2 quick examples and let's see if we can do them without looking at our graphing tool. So let's look at this first one. Remember, we have our formula, which is going to help us if we have it memorized. The a value is the number being multiplied out front, so that means it's -1. The h value is the number inside of the absolute value bars with the x. So remember, I'm going to change the sign here. Instead of saying -2, I'm going to say +2. And then the k value is the number added or subtracted outside. So that's +5. Now, with that, I know that the h value is going to be my horizontal shifts and the k value is going to be my vertical shifts instead of 0, 0. So that means that my vertex is going to be at h, k, 2, 5. So my vertex is going to be here. The h value moved it horizontally right 2 units, and the k value moved it vertically up 2 units. Oops, up 5 units. So that's my vertex, and then I have an a value of -1, which means the slope of my right hand side is going to be down 1 over 1. And my left-hand side is going to be symmetrical, so it is going to mirror that, but going to the left. So then, here is my V-shape. And I got that pretty quickly, right? I didn't have to go through the steps of the graphing. I just used my h and my k to get my vertex, and then my a value gave me my slope of my right-hand side, and I made the left-hand side match. Now, whenever we're looking at the a value, that's going to be called the dilation of the function. So because this one was just 1, it was standard. It didn't have a different slope. So I'm going to say standard here. It did open down, so we could add that and say it opens down. But when we ask about dilation, that's where we're looking for a stretch or compression or no change, which is standard. All right, let's look at this next one. The a value is the number being multiplied out front, so that's 1/2. The h value is the number inside of the absolute value with the x. Remember, we're going to change the sign on the h. That's going to be -3. And there's no number being added on the outside. So that's like saying plus nothing, plus 0. So our k value is going to be 0 in this one, since there's nothing being added outside. Our vertex then, we can get quickly because it's just hk, so it's going to be -3, 0. That means horizontally we moved left 3 units. Vertically, we didn't go up or down, so I'm going to say there's no vertical shifting happening. Now this one does have a dilation of 1/2. So I'm going to, on the right-hand side, rise 1, run 2, rise 1, run 2. Then I'm going to make my other side match. So we have a much wider V this time. It got pressed down from the top vertically, so that means we're looking at a vertical compression. Remember, we have a proper fraction for the a value, so that means we're always going to be looking at compression. This one opens up, which is normal. You could choose to say that too, but it's not part of our vertical and horizontal shifts or dilations. Okay, so I'd like for you to try a couple now. I want you to apply the knowledge of absolute value parent functions to describe the transformations and do the graphs. You should be able to do them without a graphing tool, though you can certainly use a graphing tool to check your work after you've given it an attempt.